we discovered that empty space isn't empty. It's filled with quantum fields seething with energy. But what exactly waves through those fields? Is it a particle, a wave, or something stranger, both at once, in a cosmic dance that defines all of reality, including you? Welcome back to Sleep Entangled, where quantum mysteries and contemplative wonder merge into bedtime voyages. In our journey through quantum fields, we found that space itself is alive with possibility. Tonight, we ask, what is that energy? What waves through the field? If you find depth in these explorations, remember to subscribe and let curiosity guide your nights. Now settle in, breathe slowly, and let's discover the strange double life of reality itself. Chapter 1. The question behind quantum fields. When we explored quantum fields, we discovered something profound. Empty space is not empty. It seethes with invisible fields, oceans of potential energy filling every cubic centimetre of the universe. The electron field, the photon field, the Higgs field, all interpenetrating, all vibrating with quantum uncertainty. But this raises an immediate question, one that physicists wrestled with for decades. What exactly are these fields made of? When we say the photon field, what is doing the waving? When we say the electron field, what is that field composed of? The answer is both simple and profoundly strange. Quantum fields are not made of particles, rather particles are made of quantum fields. A photon is not a thing travelling through the photon field. A photon is a localized excitation, a ripple, a wave, in the photon field itself. But then comes another question, deeper still. If particles are waves in fields, why do they sometimes behave like particles at all? Why do we detect discrete clicks in a detector, rather than smooth continuous waves? This is the heart of wave-particle duality, perhaps the most fundamental and mysterious property in all of physics. It is the idea that everything in the universe, light, matter, you, me, exists simultaneously as both wave and particle, neither fully one nor the other until measured. The story begins not with quantum fields but with light, the mystery of light. For centuries, scientists debated the nature of light. Was it a wave rippling through some invisible medium, or was it a stream of tiny particles fired like bullets from luminous sources? Isaac Newton, in the 17th century, believed light was corpuscular, made of particles he called corpuscles. This explained why light travelled in straight lines, why it cast sharp shadows, and why it bounced predictably off mirrors. But in 1801, an English polymath named Thomas Young performed an experiment that seemed to settle the debate once and for all. Young shone light through two narrow slits and observed the pattern it made on a screen beyond. If light were particles, Young reasoned, you would see two bright stripes on the screen, one behind each slit like bullets passing through two holes in a wall. But that's not what he saw. Instead, Young observed alternating bright and dark bands, an interference pattern. This is exactly what you get when waves overlap. Where two wave crests meet, they reinforce, creating brightness. Where a crest meets a trough, they cancel, creating darkness. The conclusion seemed inescapable. Light is a wave. For the next century, this wave theory dominated. James Clerk Maxwell in the 1860s unified electricity and magnetism into a single theory, and showed that light is an electromagnetic wave, oscillating electric and magnetic fields propagating through space at the speed of light. The case seemed closed. Light was a wave. End of story. But the universe had other plans. The photoelectric effect. In 1887, German physicist Heinrich Hertz discovered something puzzling. When ultraviolet light struck a metal surface, it ejected electrons. This was called the photoelectric effect, and according to wave theory, it should have been straightforward. If light is a wave carrying energy, then brighter light, higher intensity waves, should eject electrons with more energy. Dim light should still work. It would just take longer for the wave energy to accumulate and knock electrons loose. But experiments showed something completely different. Bright red light, no matter how intense, couldn't eject electrons from certain metals, but dim blue light, even at very low intensity, could. The energy of the ejected electrons depended not on the intensity of the light, but on its frequency, its colour, and there was no delay. Even extremely faint blue light ejected electrons instantly. The wave theory predicted a delay as energy accumulated, but none was observed. This was deeply strange. Waves don't behave this way. Waves spread their energy over space. A dim wave should take time to deliver enough energy to eject an electron. But the photoelectric effect happened instantly, as if light were delivering energy in discrete packets. In 1905, a young patent clerk named Albert Einstein proposed a radical solution. What if, he suggested, light is not a continuous wave but a stream of discrete packets of energy, particles of light, later called photons? Each photon carries energy proportional to the frequency of the light, E equals hf, where h is Planck's constant and f is frequency. Blue light has higher frequency than red light, so blue photons carry more energy. A single high-energy blue photon can eject an electron instantly. Low-energy red photons, no matter how many, cannot individually provide enough energy. Einstein's photon hypothesis explained the photoelectric effect perfectly. For this work, not for relativity, Einstein won the Nobel Prize in 1921. But it created a paradox. Light, it seemed, was both wave and particle. Young's experiment proved it was a wave. Einstein's photons proved it was a particle. How could it be both? The two-slit dilemma. Let's return to Young's two-slit experiment, but now with Einstein's photons in mind. Imagine we dim the light source until only one photon passes through the apparatus at a time. If photons are particles, each one must go through either the left slit or the right slit. There's no way for a single particle to go through both slits at once, so we should see two stripes on the screen, right? One stripe behind the left slit, one behind the right slit. Particle behaviour. But that's not what happens. When we perform the experiment one photon at a time and let them accumulate over hours, we still get an interference pattern, alternating bright and dark bands. Each individual photon arrives at a specific point on the screen, like a particle, but collectively they build up a wave pattern. It's as if each photon somehow goes through both slits, interferes with itself, and then lands at a single point consistent with the interference pattern. This is profoundly strange. A photon is detected as a localized click, a particle, but its behavior is guided by a wave that passes through both slits. The photon exhibits wave-particle duality. Now comes the truly bizarre part. If we place detectors at the slits to determine which slit each photon passes through, the interference pattern vanishes. Suddenly, we get two stripes, particle behavior. The act of observing which path the photon takes destroys the wave behavior. When we don't observe, the photon behaves as a wave. When we do observe, it behaves as a particle. This is not a failure of our instruments. It's a fundamental feature of reality. The photon doesn't have a definite path until we measure it. Before measurement, it exists in a superposition, a quantum combination of all possible paths interfering with itself like a wave. Measurement collapses this superposition, forcing the photon to choose one path and the wave behavior disappears. From fields to waves to particles. So, here's where we connect back to quantum fields. A photon is not a little ball of light travelling through space. A photon is an excitation in the electromagnetic field, a localized ripple, a quantum of the field. When the field is in its lowest energy state, there are no photons. When energy is added, the field ripples and we say a photon exists. But the field itself is fundamentally wave-like. It spreads through space, oscillates, interferes with itself. This is why photons exhibit wave properties. They are waves in the photon field. Yet when we detect a photon, we always find it at a specific location, with a specific energy. The detection is discrete, localized, particle-like. The wave function, the mathematical description of the field state, collapses, and the photon is found here or there but not both. Wave-particle duality is not a contradiction. It's a description of how quantum fields behave. The wave is the field state spreading through space. The particle is what we detect when the field interacts with something, when energy is localized and transferred. To see this more clearly, let's turn to matter. If light exhibits wave-particle duality, what about electrons, atoms, and everything else? As you rest tonight, imagine a photon, a single quantum of light, travelling from a distant star to your eye. It began its journey perhaps 1,000 years ago, when the star emitted a ripple in the electromagnetic field. That ripple spread through space, not as a discrete particle, but as a wave, an expanding sphere of probability. It could have gone anywhere. It could have been absorbed by dust, deflected by magnetic fields, lost in the vastness of space. But tonight, after travelling for a millennium, that ripple arrives at your retina. The wave collapses. The photon is absorbed by a molecule in your eye. Energy is transferred. A signal is sent to your brain. You see a star. The photon existed as a wave, a spread-out possibility for 1,000 years. But at the moment of detection, it became a particle, localized, real, here. This is the double life of light, and as we'll discover, it is the double life of everything. Let's slow down now and continue deeper into the mystery, where we'll find that matter itself, electrons, atoms, you, also waves through the quantum field. Chapter 2. Young's Double-Slit, the first shock. To truly understand wave-particle duality, we must return to the experiment that started it all. Thomas Young's double-slit experiment, performed in 1801, Young was not trying to revolutionize physics. He was trying to settle a debate about the nature of light. Newton had argued light was particles. Dutch physicist Christian Huygens had argued light was waves. Young wanted proof. Young's apparatus was elegantly simple. He used a coherent light source, sunlight passing through a single narrow slit to ensure all light waves started in phase. This light then encountered a barrier with two parallel slits cut into it, very close together. Beyond the slits, Young placed a screen to observe where the light landed. If light were particles, tiny bullets of luminous matter, you would expect to see two bright stripes on the screen, one behind each slit. The particles would pass through one slit or the other and accumulate in two bands. But that's not what Young saw. Instead, he observed alternating bright and dark bands, fringes spread across the screen. In the very centre, directly behind the midpoint between the two slits, there's a bright band. To either side, a dark band. Then bright again, then dark, and so on, fading as you moved away from the centre. This is an interference pattern, and it is unmistakable evidence of waves. How interference works. To understand why waves create this pattern, Imagine dropping two pebbles into a still pond. Each pebble creates concentric ripples spreading outward. Where the ripples from the two pebbles meet, they interfere. At points where two crests coincide, the waves add together, constructive interference, creating a higher crest. At points where a crest meets a trough, the waves cancel, destructive interference, creating calm water. If you placed a detector along a line in the pond, you would measure alternating regions of strong waves, constructive interference, and calm, destructive interference. This is exactly analogous to the bright and dark bands in Young's experiment. Light from the two slits acts like two coherent sources. The light waves spread out, overlap, and interfere. Where they constructively interfere, you get brightness. Where they destructively interfere, you get darkness. This pattern cannot be explained by particles. Particles don't cancel each other out. Particles don't create regions where adding more particles results in less total effect. Young's experiment seemed to prove, definitively, that light is a wave. Young's work was vindicated half a century later by James Clerk Maxwell. In the 1860s, Maxwell unified the laws of electricity and magnetism into a single elegant theory. His equations predicted that oscillating electric and magnetic fields could propagate through space as waves, travelling at a specific speed. When Maxwell calculated that speed, it matched the speed of light. The conclusion was inescapable. Light is an electromagnetic wave, oscillating electric and magnetic fields, perpendicular to each other and to the direction of travel, rippling through space at 300,000 kilometers per second. Maxwell's theory was a triumph. It explained reflection, refraction, diffraction, interference, all the behaviors of light. By the late 19th century, the wave theory of light was accepted fact, but then came the quantum revolution, Einstein's heretical photon. As we discussed in Chapter 1, Einstein's 1905 explanation of the photoelectric effect reintroduced the particle nature of light. Light, Einstein argued, is quantized, delivered in discrete packets of energy, photons, each with energy E equals hf. This was heretical. The scientific community resisted. How could light be particles when Young and Maxwell had proven it was waves? But Einstein's photon hypothesis was too successful to ignore. It explained the photoelectric effect, the spectrum of black body radiation, and a host of other phenomena that wave theory struggled with. By the 1920s, the evidence for photons was overwhelming. Light is particles, but light is also waves. Young's interference pattern doesn't go away just because Einstein proposed photons. So how do we reconcile this? The modern double-slit with photons. Let's perform Young's experiment again, but with modern equipment. We use a laser so dim that only one photon enters the apparatus at a time. We replace the screen with a photosensitive detector that records exactly where each photon lands. The first photon arrives. Click. It hits a specific point on the detector. Particle behavior. The second photon. Click. A different point. The third. Click. Another point. If you looked at just these first few photons, you'd see random dots. No pattern. Just discrete particles landing at seemingly arbitrary locations. But as hours pass and thousands of photons accumulate, a pattern emerges. The dots aren't random. They cluster into alternating bright and dark bands. The interference pattern. How is this possible? Each photon arrived individually. There was never more than one photon in the apparatus at a time. So what was each photon interfering with? The answer: itself. The photon interferes with itself. Here's the quantum mechanical explanation. Each photon, before detection, exists as a wave, a spread-out quantum state described by a wave function. This wave passes through both slits simultaneously, interferes with itself, and creates an interference pattern of probability. The wave function doesn't tell you where the photon is, it tells you where the photon might be found when measured. The wave function squared gives the probability density for finding the photon at each location. Where the wave function has constructive interference, the probability is high, bright bands form. Where it has destructive interference, the probability is low or zero, dark bands form. When the photon is detected, the wave function collapses. The photon is found at a single location, consistent with the probability distribution. It arrives as a particle, a localized click, but its probability of arriving at that location was determined by wave interference. So the photon is not a particle traveling through one slit, nor is it a wave spreading through both slits. It is something else, a quantum object that exhibits both properties depending on how we observe it. Which path information destroys interference? Now comes the most astonishing part. Suppose we modify the experiment to determine which slit each photon passes through. We place detectors at the slits, perhaps sensors that register when a photon goes by without absorbing it. We run the experiment again. This time the detector tells us photon 1 went through the left slit, photon 2 went through the right slit, photon 3 went through the left slit, and so on. We let thousands of photons accumulate. We look at the final pattern on the screen, and the interference pattern is gone. Instead, we see two bright stripes, one behind each slit. Pure particle behavior, as if the photons are bullets passing through one slit or the other. What happened? By determining which slit each photon passed through, by gaining which path information, we destroyed the coherence of the wave function. The photon can no longer be in a superposition of passing through both slits. It must be in a definite state, left slit or right slit. Without superposition, there's no interference, no wave behavior, just particles. This is not a defect of our detectors, it's a fundamental principle. The act of measurement, of interacting with the photon to determine its path, collapses the wave function. The photon is forced to choose one slit, and the wave-like spreading through both slits is destroyed. Quantum mechanics is clear. You cannot have which path information and interference at the same time. It's not that we're clumsy or our instruments are imperfect. Nature itself forbids it. If you know which slit the photon went through, the interference vanishes. If you preserve the interference, you cannot know which slit it went through. This is called complementarity, a principle formulated by Niels Bohr. Wave and particle behaviors are complementary, mutually exclusive ways of observing the same quantum system. You can measure one or the other, but never both simultaneously. The delayed choice experiment. In the 1970s, physicist John Archibald Wheeler proposed an even stranger variation, the delayed choice experiment. What if we wait until after the photon has passed through the slits before deciding whether to measure which path information? Common sense says the photon should have already decided whether to behave as a wave or a particle. Once it's through the slits, its fate should be sealed. But quantum mechanics predicts otherwise, and experiments confirmed Wheeler's prediction. Even if you choose to measure which path information after the photon has passed the slits, but before it hits the screen, the interference pattern disappears. Conversely, if you choose not to measure, interference appears. It's as if the photon retroactively knew what kind of measurement would be performed and adjusted its behavior accordingly. Of course, no information travels backward in time. The photon doesn't know anything. Rather, the wave function encompasses all possibilities, and only at the moment of measurement does it collapse into a specific outcome consistent with the type of measurement performed. The universe waits for you. Universe. The delayed choice experiment suggests something profound. The photon doesn't exist in a definite state until it's measured. Before measurement, it's in a superposition, a quantum blur of both wave and particle, both paths, neither fully real until observed. This isn't just about photons, it's about reality itself. Quantum mechanics suggests that properties of objects, position, momentum, path, don't have definite values until measured. The universe is not a collection of definite things with definite properties. It's a web of potentialities, collapsing into actuality moment by moment through observation. We are not passive observers of a pre-existing reality. We are participants in bringing reality into being. So, imagine this. The light falling on your face right now began as waves in the electromagnetic field. Those waves spread through space, interfering, diffracting, carrying probability. But the moment they touched your skin, the wave collapsed. Photons became real, transferring energy, warming you, illuminating the world around you. Every photon you've ever seen followed this strange double life. Wave as it travelled, particle as it arrived. Reality itself flickers between potential and actual, waiting for the moment of observation to crystallize into the solid, definite world you experience. This is not a flaw in nature, it is nature, and it applies not just to light, but to everything. Now let us turn to matter. If photons are waves in the electromagnetic field, could electrons, solid, massive particles, also wave? Chapter 3, Einstein's revolutionary photon. Stuckjaw. Before we explore whether matter can wave, let's deepen our understanding of the photon itself. Einstein's 1905 paper didn't just explain the photoelectric effect, it challenged the entire framework of classical physics and opened the door to the quantum revolution. To appreciate Einstein's insight, we must first understand the problem he was trying to solve. In the late 19th century, physicists studied blackbody radiation, the spectrum of light emitted by hot objects. Heat a metal rod and it glows red, then orange, then white as it gets hotter. This glow is electromagnetic radiation, and its spectrum depends on temperature. Classical physics predicted that hot objects should emit radiation at all frequencies, with intensity increasing toward higher frequencies. This was called the Rayleigh-Jeans law. But this led to an absurd conclusion. According to the Rayleigh-Jeans law, the intensity should keep increasing without limit toward ultraviolet and beyond, meaning every hot object should emit infinite energy at high frequencies. This was called the ultraviolet catastrophe. Obviously, hot objects don't emit infinite energy, so something was wrong with classical physics. In 1900, German physicist Max Planck found a solution. He proposed that electromagnetic energy is not emitted continuously, but in discrete chunks, quanta, with energy proportional to frequency. E equals hf, where h is Planck's constant, 6.626 times 10 to the negative 34th joule seconds, and f is frequency. This quantization meant that high-frequency radiation requires large energy quanta. At high frequencies, the energy gap is so large that it becomes statistically unlikely for an atom to emit such a quantum. This naturally suppresses high-frequency radiation, solving the ultraviolet catastrophe. Planck's formula fit experimental data perfectly, but Planck himself didn't believe quantization was real. He thought it was a mathematical trick, a way to make the equations work. He spent years trying to derive his formula without quantization, hoping to reconcile it with classical physics. He failed. Quantization was real, Einstein takes it. Further, Einstein saw something Planck didn't. If energy is emitted in quanta, then perhaps light itself is quantized. Not just the emission process, but the light itself exists as discrete packets of energy. This was radical. Maxwell's electromagnetic wave theory was well established, beautiful, and successful. To suggest that light is actually particles was to question decades of accepted science, but Einstein, then 26 years old and working in a patent office, was not constrained by academic orthodoxy. He followed the logic wherever it led. The photoelectric effect explained. Recall the puzzle. When light strikes a metal surface, electrons are ejected, but only if the light frequency is above a certain threshold. Intensity doesn't matter, frequency does, and there's no delay. Even faint light ejects electrons instantly. Einstein's explanation. Light consists of photons, each carrying energy E equals hf. When a photon strikes an electron in the metal, it can transfer all its energy to that electron. If the photon energy exceeds the work function, the energy needed to free the electron from the metal, the electron is ejected. High frequency, blue UV photons have enough energy. Low frequency, red, photons don't, no matter how many of them there are. Brightness increases the number of photons, not the energy per photon, so bright red light still can't eject electrons from metals with high work functions. And there's no delay because the interaction is instantaneous. One photon, one electron, direct energy transfer. The electron doesn't wait for wave energy to accumulate. It either gets hit by a sufficiently energetic photon or it doesn't. Einstein's formula matched experiments perfectly. KE equals hf minus phi, where Ke is the kinetic energy of the ejected electron, hf is the photon energy, and phi is the work function of the metal. The physics community resists. You might think the physics community embraced Einstein's photon immediately. They didn't. The wave theory of light was too well established. Interference, diffraction, polarization, all beautifully explained by waves. To throw that away for particles seemed reckless. Prominent physicists, including Planck himself, rejected Einstein's photons. They agreed light emission was quantized, but argued light itself was still a continuous wave. It took nearly 2 decades for Einstein's photon to be accepted. The turning point came in 1923 when American physicist Arthur Compton demonstrated that photons carry momentum and collide with electrons like billiard balls, a phenomenon called Compton scattering. Compton's experiments show that photons not only carry quantized energy, but also behave as particles with definite momentum. P equals h over lambda, where p is momentum and lambda is wavelength. This was undeniable. Photons have particle-like properties, discrete energy, definite momentum, localized interactions. Einstein was right, but Young's interference experiment was also right. Light is waves. The paradox deepened. Bohr and Einstein debate. Throughout the 1920s and 30s, Niels Bohr and Albert Einstein engaged in a famous series of debates about the interpretation of quantum mechanics. Bohr defended the Copenhagen interpretation, which embraced wave-particle duality as fundamental. According to Bohr, it makes no sense to ask whether a photon really is a wave or a particle. It exhibits wave behavior in some experiments, particle behavior in others. The behavior depends on the measurement setup. Bohr introduced the concept of complementarity. Wave and particle are complementary descriptions. They're never both observed simultaneously. Which aspect you see depends on which experiment you perform. Einstein hated this. He famously said, "God does not play dice. rejecting the idea that nature is fundamentally probabilistic. Einstein believed there must be a deeper, deterministic reality underlying quantum mechanics, hidden variables that, if known, would remove the randomness and restore classical certainty. Bohr countered that Einstein was clinging to outdated notions of reality. Quantum mechanics, Bohr argued, is complete. There are no hidden variables. The probabilistic, complementary nature of quantum phenomena is reality, not ignorance. This debate was never fully resolved in their lifetimes, but experiments decades later, particularly tests of Bell's inequality, have strongly favoured Bohr's view. Nature really is fundamentally quantum, fundamentally probabilistic, fundamentally non-classical. The photon in quantum field theory. Modern physics has resolved the wave-particle duality paradox, at least conceptually, through quantum field theory. In this framework, the fundamental entity is not the photon as a particle, nor light as a wave, but the electromagnetic field itself. This field permeates all of space, existing even in vacuum. The field has a lowest energy state, the ground state or vacuum state. When energy is added, the field is excited. A single quantum of excitation is what we call a photon. The field itself is wave-like. It has amplitude, phase, and can interfere. This explains wave behaviors like interference and diffraction. But when the field interacts with matter, when it's measured, energy is exchanged in discrete quanta. This explains particle behaviors like localized clicks in detectors and the photoelectric effect. So the photon is neither wave nor particle. It's an excitation in a quantum field, exhibiting properties of both depending on how we interact with it. This doesn't resolve all the mystery. We still don't fully understand why measurement causes the field's wave-like state to collapse into a localized particle-like event. But it provides a framework, a language, for describing what happens. Why does light behave this way? Is there a deeper reason why light must be quantized? Why can't electromagnetic energy be continuous? The answer may lie in the structure of space-time itself. Some theories suggest that space-time is not infinitely divisible, but has a fundamental granularity at the Planck scale, about 10 to the negative 35th meters. If space and time are quantized, made of discrete units, then fields living in space-time might also be quantized. Energy, momentum, and angular momentum would come in discrete packets because the underlying geometry is discrete. This is speculative. We don't yet have a complete theory of quantum gravity to confirm it, but it's possible that quantization is not arbitrary. It's a reflection of the discrete nature of reality itself at the smallest scales. Or perhaps quantization emerges from some deeper principle we don't yet understand. Quantum field theory works beautifully, predicting phenomena to extraordinary precision, but we don't know why it's true. We describe how nature behaves, but the why remains elusive. The photon as reality's messenger. Every photon you've ever seen, from this screen, from the sun, from distant stars, carried information. It began as an excitation in the electromagnetic field, spread through space as a wave of probability, and collapsed into a localized event when it reached your eye. In that moment, potential became actual. Probability became reality. The wave function collapsed, and you experienced light. This is how information travels in the universe. Electromagnetic waves, photons, connect everything. They carry energy, momentum, and information across space, binding together atoms, planets, galaxies, and consciousness. And it all began with Einstein's radical idea. Light is not a continuous wave. It is quantized. It is both wave and particle, neither fully real until observed. A moment of reflection. So as you rest now, consider the light around you, the soft glow of this screen, the lamp beside your bed, the starlight filtering through your window. All of it is quantum. All of it waves. All of it collapses into discrete moments of reality as it reaches you. You're not observing a pre-existing world. You're collapsing wave functions moment by moment, bringing reality into focus through the simple act of perception. And if light, massless, ethereal light, behaves this way, what about matter? What about electrons, atoms, your own body? Could they also wave? Let us find out. Chapter 4. De Broglie's Matter Waves. In 1923, a young French aristocrat and physicist named Louis de Broglie made a proposal so audacious, so seemingly absurd, that even his doctoral thesis committee wasn't sure whether to accept it. De Broglie proposed that if light, traditionally thought of as a wave, can behave as particles, photons, then perhaps matter, traditionally thought of as particles, can behave as waves. Everything, de Broglie suggested, has a wavelength. This idea seemed crazy. Electrons are particles. They have mass, charge, and definite location. They collide with things. They leave tracks in cloud chambers. How could a particle possibly be a wave? But de Broglie had a compelling argument, rooted in symmetry. The symmetry argument Einstein had shown that photons, despite being massless, carry momentum. P equals E over C equals HF over C equals H over lambda, where P is momentum, E is energy, C is the speed of light, F is frequency, and lambda is wavelength. De Broglie asked, if waves, light, have particle properties, momentum, shouldn't particles, matter, have wave properties, wavelength? He proposed that every particle with momentum p has an associated wavelength, lambda equals h over p. This is now called the de Broglie wavelength. For a particle of mass m moving at velocity v, the momentum is p equals mv, so lambda equals h divided by mv. This is a simple, beautiful formula, and it makes a testable prediction. For macroscopic objects, the de Broglie wavelength is absurdly small. A baseball thrown at 40 meters per second has a wavelength of about 10 to the negative 34th meters, far smaller than an atom. Such tiny wavelengths produce no observable wave effects. The baseball behaves purely as a particle, but for electrons, which have tiny mass and typically move at speeds comparable to light, the wavelength is significant, on the order of nanometers, comparable to the spacing between atoms in a crystal. If electrons really are waves, we should be able to observe interference and diffraction, the hallmarks of wave behavior. When de Broglie submitted his thesis in 1924, the committee was skeptical. The idea was so strange that they sent it to Einstein for review. Einstein replied that de Broglie's work was not only correct, but had lifted a corner of the great veil. Emboldened by Einstein's endorsement, the committee awarded de Broglie his doctorate, but the physics community remained unconvinced. Matter waves were a mathematical curiosity, not reality. Then, 3 years later, came proof. The Davison-Germer experiment. In 1927, American physicists Clinton Davison and Lester Germer were studying how electrons scatter off nickel surfaces. Their goal was purely practical, understanding electron-metal interactions for industrial applications. During one experiment, an accident occurred. A flask of liquid air exploded, exposing the nickel target to air. The surface oxidized and had to be cleaned by heating. Unknown to Davison and Germer, this heating caused the nickel to form large single crystals, regions where atoms are arranged in regular repeating patterns. When they resumed the experiment, something unexpected happened. Instead of scattering uniformly in all directions, the electrons scattered in specific directions with intensity peaks at particular angles. This looked exactly like X-ray diffraction, a well-known wave phenomenon where X-rays, electromagnetic waves, scatter off crystal lattices and interfere, producing characteristic patterns. Davison and Germer had accidentally demonstrated electron diffraction. They calculated the angles and intensities of the scattered electrons and found they matched the prediction of de Broglie's formula perfectly. The electrons were behaving as waves with wavelength lambda equals h/p, interfering constructively and destructively as they scattered off the regular array of atoms in the crystal. Electrons, particles with mass and charge, were waves. The same year, British physicist George Paget Thomson, son of J.J. Thomson, who discovered the electron as a particle, independently confirmed electron diffraction by passing electrons through thin metal foils. The evidence was overwhelming. De Broglie was right. Diffraction patterns. Electron diffraction works just like X-ray diffraction. A crystal is a regular array of atoms spaced by a distance d. When a wave encounters this array, it scatters off each atom. The scattered waves interfere. At certain angles, the path difference between waves scattered from adjacent atoms is an integer multiple of the wavelength. These waves interfere constructively, producing bright spots. At other angles, destructive interference occurs, producing dark regions. The resulting pattern, rings or spots on a detector, is called a diffraction pattern. It's unmistakable evidence of wave behavior. Davison and Germer's experiments showed that electrons, when passed through or reflected off crystals, produce diffraction patterns consistent with de Broglie's wavelength formula. This could not be explained if electrons were simply particles. Thomson's experiment extended this, showing that electrons passing through thin foils produce ring patterns similar to those produced by X-rays. Again, unmistakable wave behavior. For their discoveries, Davison and Thomson shared the 1937 Nobel Prize in Physics. De Broglie had won his Nobel Prize in 1929, the first person ever awarded the prize for a doctoral thesis. Matter waves in everyday devices. Electron diffraction is not just a laboratory curiosity, it's used in technology. The transmission electron microscope, TEM, invented in the 1930s, uses electron waves to image materials at atomic resolution. Because electron wavelengths are much shorter than visible light, TEMs can resolve features thousands of times smaller than optical microscopes. This technology has been essential for nanotechnology, materials science and biology, allowing scientists to see individual atoms. The very fact that we can use electrons as waves to image the world is proof that matter waves are real. Interference of atoms and molecules. If electrons wave, what about atoms, molecules, larger objects? In 1930, German physicists Otto Stern and Emanuel Estermann demonstrated the diffraction of helium atoms. Later experiments showed diffraction of hydrogen, neutrons, and even complex molecules. In 1999, Austrian physicist Anton Zeilinger and colleagues demonstrated the interference of C60 fullerene molecules, buckyballs containing 60 carbon atoms. These molecules, each containing 720 protons, neutrons and electrons, passed through a diffraction grating and produced an interference pattern. Molecules hundreds of times more massive than a proton exhibited wave behavior. More recently, experiments have demonstrated interference of molecules containing over 800 atoms. The larger the molecule, the smaller its de Broglie wavelength, and the harder it is to observe interference, but it's there. In principle, everything waves. You, me, this planet, all have de Broglie wavelengths. The wavelengths are just so fantastically small that wave effects are completely negligible. For a human weighing 70 kilograms moving at 1 meter per second, the de Broglie wavelength is about 10 to the negative 36 meters, a billion times smaller than a proton. Such minuscule wavelengths produce no observable effects. We behave purely as particles, but fundamentally we are waves. What does it mean for matter to wave? Here's where the interpretation becomes subtle. When we say an electron is a wave, what exactly is waving? It's not a ripple in space like a water wave. It's not an oscillating field like light. It's something stranger, a wave of probability. The wave function, usually denoted C, is a mathematical object that describes the quantum state of a particle. The wave function itself is not directly observable, but its square, vertical bar psi vertical bar squared gives the probability density, the likelihood of finding the particle at a given location if you measure it. Where the wave function is large, the probability is high. Where it's small, the probability is low. Where the wave function interferes constructively, you're likely to find the particle. Where it interferes destructively, you won't find the particle at all. So when we say an electron is a wave, we mean its probability of being found in various locations is described by a wave function that can spread, diffract, and interfere. The electron doesn't exist at a definite location before measurement. It exists in a superposition, a quantum blur, spread over all possible locations, with amplitudes given by the wave function. Measurement collapses this wave function, and the electron is found at a specific location with probability determined by PS2, Schrödinger's equation. In 1926, Austrian physicist Erwin Schrödinger formulated the equation that governs how matter waves evolve over time. Schrödinger's equation is to quantum mechanics what Newton's laws are to classical mechanics, the fundamental equation of motion. For a particle in a potential v of x, Schrödinger's equation is IH bar partial psi over partial t equals negative h bar squared over 2m partial squared psi over partial x squared plus v of x psi. This looks complicated, but it's essentially a wave equation. It describes how the wave function psi changes over time, spreading, interfering, and evolving according to the forces acting on the particle. Schrödinger's equation is extraordinarily successful. It predicts the energy levels of atoms, the behavior of electrons in materials, the properties of molecules, and countless other phenomena with stunning accuracy. But it's a wave equation. It treats particles as waves, and that leads to all the strange behaviors we've been discussing: interference, superposition, uncertainty. De Broglie's legacy, Louis de Broglie's insight that matter has wavelength, was one of the most important ideas in the history of physics. It extended wave-particle duality from light to matter, revealing that duality is a fundamental feature of nature, not a quirk of photons. De Broglie's hypothesis directly inspired Schrödinger to develop wave mechanics, which became the foundation of quantum mechanics. It led to the electron microscope, quantum chemistry, solid-state physics, and modern technology. And it raised a profound question. If everything is fundamentally a wave, why does the world appear solid and definite? We'll explore that question later. For now, let us pause and let this strange truth settle. As you rest tonight, imagine yourself not as a solid object but as a wave, a vast, spread-out quantum wave function, with amplitudes extending through space, interfering with the waves of everything around you. Your atoms, each one, has a de Broglie wavelength. Your electrons wave through their orbitals, not as particles in fixed paths, but as probability clouds, blurring into each other, interfering, creating the stable patterns we call matter. You are not solid. You are a wave, temporarily localized by constant interaction with your environment, collapsing and recollapsing moment by moment into the definite form you perceive, and so is everything else. Let us continue deeper, where we will see how these matter waves were confirmed beyond doubt. Chapter 5. The electron's wavelength revealed. The discovery of electron diffraction was not just a triumph for de Broglie's theory, it was a turning point in physics, marking the moment when quantum mechanics transitioned from mathematical abstraction to experimental reality. Let us explore the experiments in detail, for they reveal not just that electrons wave, but how they wave, and what that means for our understanding of reality. Crystal lattices as gratings. To understand electron diffraction, we must first understand how crystals scatter waves. A crystal is a regular, repeating array of atoms. Nickel, for instance, forms a face-centered cubic lattice, where atoms are arranged at the corners and face centers of cubic cells, with spacing around 0.35 nanometers. When a wave encounters this lattice, it scatters off each atom. The scattered waves propagate in all directions, but they interfere. At certain angles, the waves from different atoms are in phase. They add constructively. At other angles, they're out of phase. They cancel destructively. This is analogous to a diffraction grating, a device with many parallel slits used to separate light into colors. The regular spacing of slits, or atoms, causes waves of different wavelengths to interfere constructively at different angles, creating a pattern of bright and dark bands, or spots. For X-rays, which have wavelengths comparable to atomic spacing, crystal diffraction is well established. X-ray crystallography, pioneered by Max von Laue and the Braggs in the 1910s, uses this principle to determine crystal structures. Davison and Germer's discovery was that electrons behave the same way. Electrons with de Broglie wavelengths comparable to X-ray wavelengths diffract off crystal lattices, producing patterns consistent with wave interference. Davison and Germer's apparatus was relatively simple. They accelerated electrons to a known energy, and thus momentum and de Broglie wavelength, directed them at a nickel crystal, and measured the intensity of scattered electrons at various angles. If electrons were classical particles, they would scatter uniformly in all directions, or perhaps preferentially in the forward direction, depending on the collision dynamics. There should be no dependence on wavelength because particles don't have wavelength. But what they observed was completely different. At certain angles, the scattered electron intensity was much higher than at others. These intensity peaks occurred at angles that depended on the electron energy, and thus wavelength. When they calculated the angles using Bragg's law for wave diffraction, n lambda equals 2d sine theta, where n is an integer. Lambda is the wavelength, d is the atomic spacing, and theta is the scattering angle. They found perfect agreement with the observed peaks. If they used de Broglie's wavelength, lambda equals h over p, the electrons were behaving as waves with the exact wavelength predicted by de Broglie. There was no alternative explanation. The electrons were not bouncing off atoms like billiard balls. They were interfering as waves, with the crystal lattice acting as a natural diffraction grating. George Paget Thomson's experiment provided complementary evidence. Instead of reflecting electrons off a crystal surface, he transmitted them through thin metal foils, polycrystalline materials composed of many tiny randomly oriented crystals. When X-rays pass through such foils, they produce ring patterns on a detector behind the foil. Each ring corresponds to a specific diffraction angle, averaged over all crystal orientations, Thomson found that electrons did the same. When he passed a beam of electrons through a thin gold foil, he observed concentric rings on a photographic plate, exactly the pattern expected for wave diffraction. Again, the ring spacing matched the prediction of de Broglie's wavelength formula. Interestingly, Thomson's father, J.J. Thomson, had won the Nobel Prize in 1906 for proving that electrons are particles. George Thomson won the Nobel Prize in 1937 for proving that electrons are waves. This is a beautiful illustration of wave-particle duality. Electrons exhibit both behaviors depending on the experiment. Neutron diffraction. If electrons wave, what about other particles? In 1936, German physicists demonstrated the diffraction of neutrons. Neutrons, unlike electrons, have no charge. They're affected only by the strong nuclear force and gravity. But they still have mass and momentum, so they should have a de Broglie wavelength. Neutron diffraction works similarly to electron diffraction. Neutrons scatter off the nuclei of atoms in a crystal, and the scattered waves interfere. Because neutrons interact differently with different isotopes, neutron diffraction provides complementary information to X-ray crystallography. Today, neutron diffraction is a standard tool in materials science and biology, used to study magnetic structures, hydrogen positions in molecules, which X-rays can't easily detect, and protein structures. In the 1990s, physicists extended wave interference to entire atoms. Atom interferometers use the wave nature of atoms to make extraordinarily precise measurements of gravity, rotation, and fundamental constants. The basic idea: split an atomic wave function into two paths. Let the paths travel through space experiencing different conditions, like gravitational fields, then recombine them. The paths interfere, and the interference pattern reveals tiny differences in what the atoms experienced. Atom interferometers have achieved precisions exceeding 1 part in 10 to the 11th power, making them among the most sensitive instruments ever built. They're used to measure the fine structure constant, search for gravitational waves, and test general relativity. The very existence of atom interferometry confirms that atoms, made of protons, neutrons, and electrons, each themselves waving, behave as coherent quantum waves. The double-slit with electrons. In 1961, German physicist Klaus Jönsson performed the ultimate test, Young's double-slit experiment with electrons. Jönsson directed a beam of electrons at a barrier with 2 narrow slits, each just a few micrometers wide. Beyond the slits, he placed a detector screen. The result: an interference pattern. Just like photons, electrons passing through 2 slits produced alternating bright and dark bands. And like photons, when Jönsson sent electrons through one at a time, they still produced an interference pattern, each electron interfering with itself. More recently, in 2013, physicists at the University of Nebraska-Lincoln performed a high-resolution version of this experiment, capturing stunning images of the electron interference pattern building up particle by particle. Each electron arrives as a single point, a particle, but collectively they form a wave pattern. The electron is neither fully wave nor fully particle, it's both. The matter-wave microscope. The wave nature of matter isn't just physics curiosity, it's the foundation of modern technology. Electron microscopes, invented in the 1930s and refined over decades, use electron waves to image materials at atomic resolution. Because the de Broglie wavelength of electrons accelerated to high energies is far shorter than visible light, electron microscopes can resolve features thousands of times smaller than optical microscopes. Scanning electron microscopes, SEMs, and transmission electron microscopes, TMs, are essential tools in nanotechnology, material science, biology, and medicine. They've allowed us to see viruses, study the structure of materials at the nanoscale, and manipulate individual atoms. Every image from an electron microscope is a testament to wave-particle duality. The image is formed because electrons wave, diffract, and interfere, yet they're detected as discrete particles, building up an image pixel by pixel. Why does matter wave? So we've established beyond any doubt that matter waves, electrons, neutrons, atoms, molecules, all exhibit wave properties when tested appropriately. But why? What's the physical reason? The answer, according to quantum field theory, is that particles aren't fundamental. Fields are fundamental. An electron is an excitation in the electron field. A proton is a bound state of quark fields. A neutron is similar. These fields are wave-like. They have amplitude, phase, and can interfere. So excitations in these fields, what we call particles, inherit wave properties from the fields themselves. When an electron moves through space, it's not a little ball travelling a path. It's a localized wave packet in the electron field, spreading and interfering as it propagates. This is why de Broglie's formula works. The wavelength lambda equals h over p emerges naturally from the quantum field theory of electrons. It's not a separate assumption. It's a consequence of the field's dynamics. If you wanted to, you could think of particles as being waves in fields, and particles as what we detect when we measure the field's state. Both descriptions are valid. They're complementary ways of describing the same underlying reality. Why don't we see everyday objects wave? If everything waves, why don't we see cars, people, or planets exhibiting interference? The answer is decoherence, which we'll explore in depth later. But the short version: large objects interact constantly with their environment. Air molecules, photons, gravitational fields. These interactions constantly measure the object's position, collapsing its wave function billions of times per second. Additionally, the de Broglie wavelength of macroscopic objects is absurdly small. For a car, it's smaller than 10 to the negative 38th meters, far smaller than anything measurable. Such tiny wavelengths produce no observable wave effects, so while macroscopic objects are, fundamentally, waves, they behave classically for all practical purposes. The wave nature is hidden by decoherence and drowned out by the object's enormous mass. But at the quantum scale, electrons, atoms, small molecules, wave behavior dominates. And that's the scale on which chemistry, biology, and nanotechnology operate. We are made of waves, even if we don't wave as a whole. As you settle deeper now, imagine the electrons in your body. Trillions upon trillions of them, each one a wave, each one spread over space, each one interfering with itself and others. These waves form orbitals around atomic nuclei, not fixed paths, but probability clouds, regions where the electron is likely to be found. The orbitals overlap, creating bonds, molecules, proteins, cells, you. You're a structure built from wave interference. The solidity you feel is not particles clicking together like Lego bricks. It's wave functions reinforcing in specific regions, creating stable patterns of high probability density. And those patterns shift, flow, rearrange billions of times per second as chemical reactions, metabolic processes, and neural activity ripple through you. You are not a thing, you are a process, a wave, temporarily coherent, interfacing with the world. Now, let us turn to the question of how these strange wave and particle properties coexist. If you're still with me in this late-night exploration of quantum reality, you're part of something rare. a community of seekers willing to drift through the deepest mysteries of existence. A quick subscribe helps others discover this peaceful journey where science and serenity merge. Now, let's continue deeper into the quantum world, where we'll discover how Niels Bohr resolved the paradox of wave and particle. Chapter 6. Complementarity. Bohr's resolution. By the mid-1920s, the evidence was overwhelming. Light and matter exhibit both wave and particle properties. But how could this be? How can something be both a wave and a particle? These seem fundamentally incompatible. A particle is localized. It exists at a specific point in space. A wave is extended. It spreads over a region. A particle has definite position. A wave has definite wavelength. Position and wavelength are mutually exclusive in classical physics. The resolution came from Niels Bohr, the Danish physicist whose Copenhagen interpretation of quantum mechanics became the standard view, at least in the early decades. Bohr's principle of complementarity states that wave and particle are not contradictory but complementary descriptions of quantum systems. They are both valid, but they cannot be observed simultaneously. Which aspect you see depends on how you choose to observe. This was a radical departure from classical physics, where objects have definite properties independent of observation. In quantum mechanics, the act of observation is not passive. It determines which properties manifest. Let us explore this carefully. The complementarity principle. Imagine you want to measure the position of an electron. You shine light on it, and a photon scatters off the electron into your detector. The scattered photon tells you where the electron was at the moment of scattering, particle-like behavior. But the interaction with the photon disturbs the electron. The photon transfers momentum to the electron, changing its velocity. So while you've measured position precisely, you've lost information about momentum and thus wavelength. Now imagine you want to measure the electron's wavelength. You set up an interference experiment with two slits. The electron passes through, interferes with itself, and produces an interference pattern. From the pattern, you can deduce the wavelength, wave-like behavior. But to see interference, you must not measure which slit the electron passed through. If you try to determine the electron's position, which slit, you destroy the interference and lose the wavelength information. This is complementarity. Position and wavelength, particle and wave, are complementary properties. You can measure one or the other, but never both simultaneously with arbitrary precision. It's not that we lack clever enough instruments. Nature itself forbids it. The uncertainty principle. Werner Heisenberg, Bohr's younger colleague, formalized this into the uncertainty principle. Dx depth greater than or equal to h over 2, where dx is the uncertainty in position, dp is the uncertainty in momentum, and h bar is the reduced Planck constant, r bar equals h over 2pi. This states that the product of position and momentum uncertainties has a lower bound. The more precisely you know position, the less precisely you can know momentum, and vice versa. This is not a statement about measurement error. It's a fundamental limit imposed by the wave nature of matter. Position and momentum don't have simultaneous definite values. The particle doesn't have a precise position and momentum. It has a wave function that encodes probabilities for both. If you measure position, you collapse the wave function into a narrow spatial region, high position precision, low momentum precision. If you measure momentum, or wavelength, you collapse the wave function into a definite momentum state, high momentum precision, low position precision, low position precision. Heisenberg's principle is a direct consequence of wave-particle duality. Waves have wavelength, related to momentum but are spread out. indefinite position. Localized particles have definite position but indefinite wavelength. You can't have both. Let's return to the double-slit experiment and apply complementarity. Setup 1. Know which path information. You send electrons through 2 slits and observe the screen. You see an interference pattern, wave behavior. The electrons are in a superposition of passing through both slits. You have wavelength information from the fringe spacing, but no position information. You don't know which slit each electron passed through. Setup 2. Which path detection. You place detectors at the slits to measure which slit each electron passes through. Now you have position information. You know the electron went through slit A or slit B. But the interference pattern vanishes. You lose the wavelength information. Particle behavior dominates. These are complementary setups. You can choose to observe wave properties or particle properties, but not both simultaneously. Importantly, you can't cheat. If you try to make a weak measurement that only partially determines which slit, the interference pattern only partially degrades. The more which path information you gain, the more interference you lose. Nature maintains a perfect balance. Complementarity is preserved. Einstein never accepted complementarity. He believed quantum mechanics was incomplete, that there must be some deeper reality beneath the probabilities, some hidden variables that determine outcomes in advance. In 1930, at the 6th Solvay Conference, Einstein proposed a thought experiment designed to violate the uncertainty principle. He described a box containing a photon with a shutter controlled by a clock. The shutter opens briefly, releasing the photon. By weighing the box before and after, you can determine the photon's energy via E equals mc squared. By reading the clock, you know exactly when it was released. This seems to violate the energy-time uncertainty relation. Bohr spent a sleepless night pondering Einstein's challenge. The next morning he presented a solution. According to general relativity, time runs at different rates in gravitational fields. The act of weighing the box involves it moving up or down in Earth's gravitational field, which introduces an uncertainty in the clock's rate. When you account for this relativistic effect, the energy-time uncertainty relation is preserved. Einstein conceded the point, but he remained unconvinced that quantum mechanics was complete. Years later, Einstein famously remarked, "I cannot believe that God plays dice with the universe." Bohr's reply, "Einstein, stop telling God what to do." The EPR paradox. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics is incomplete. They presented a thought experiment now known as the EPR paradox. The idea: create 2 particles in an entangled state, then separate them by a large distance. Measure one particle's position precisely. According to quantum mechanics, this instantaneously determines the other particle's position due to entanglement, even though no signal can travel faster than light between them. Similarly, you could instead measure one particle's momentum, which would determine the other's momentum. So both position and momentum of the distant particle seem to have definite values, waiting to be revealed by your choice of measurement. But quantum mechanics says they can't both have definite values simultaneously. Einstein argued this meant quantum mechanics is incomplete. There must be hidden variables that predetermine the measurement outcomes. The particles carry complete information, even if quantum mechanics doesn't describe it. Bohr's response was subtle. He argued that the properties of the distant particle don't exist independently until measured. The measurement on one particle brings into being the property of the other. There's no contradiction because properties don't pre-exist measurement, they emerge from measurement. This debate remained unresolved for decades. But in 1964, physicist John Bell derived an inequality that could test whether hidden variables exist. Experiments testing Bell's inequality, starting in the 1970s and refining through the 2010s, have consistently supported quantum mechanics and ruled out local hidden variables. Nature really is complementary, non-local, and probabilistic at its core. What does complementarity mean? Complementarity is not just a technical detail. It's a profound statement about the nature of reality. In classical physics, objects have definite properties: position, momentum, energy. These properties exist independent of observation. Measurement reveals what was already there. In quantum mechanics, this is not true. Properties don't exist in definite form until measured. Before measurement, the system is in a superposition, a quantum blur of multiple possible states. Measurement forces the system to choose one outcome, but the choice is probabilistic. Which property you measure determines which aspect of the system manifests. Measure position, and you collapse the wave function into a localized particle-like state. Measure momentum or wavelength, and you collapse it into a delocalized wave-like state. The system doesn't have both properties waiting to be revealed. It has potential for both, and measurement actualizes one at the expense of the other. This is complementarity. Wave and particle, position and momentum are complementary ways of interacting with the quantum system. Neither is more real than the other. Both are real, but not simultaneously observable. What does this mean for our understanding of reality? One interpretation: reality is not observer-independent. Properties emerge through the interaction between quantum systems and measurement apparatuses, which include us. Before measurement, there are only probabilities, not definite outcomes. Another interpretation: reality is fundamentally relational. Objects don't have properties in isolation. They have properties relative to other systems they interact with. An electron has position relative to a measuring device, momentum relative to another device, but these properties are not absolute. They depend on the interaction. Some interpretations, like many worlds, reject the idea of collapse entirely. They say all possible outcomes occur, each in a separate branch of reality. Complementarity then becomes a statement about which branch you end up in. But regardless of interpretation, the experimental fact remains. Wave and particle behaviors are complementary. You see one or the other, never both, depending on your experimental setup. Bohr's principle of complementarity shaped the Copenhagen interpretation, which dominated physics for decades. It's pragmatic. Focus on what can be measured, don't speculate about unmeasurable realities beneath the quantum formalism, and accept that nature is fundamentally probabilistic. This approach has been enormously successful. Quantum mechanics works. It predicts phenomena with staggering accuracy. Modern technology, semiconductors, lasers, MRI machines, quantum computers, relies on quantum mechanics. But Bohr's philosophy remains controversial. Many physicists find it unsatisfying to say that properties don't exist until measured. They seek deeper explanations, pilot wave theories, many worlds, objective collapse models. Yet all these alternatives must reproduce complementarity. Whatever reality ultimately is, it must exhibit wave-particle duality when probed appropriately. That's not interpretation, that's experimental fact. So, as you rest, consider this. You are made of particles, electrons, protons, neutrons. But those particles are also waves spreading through space, interfering, superposing. Which aspect you see depends on how you interact with them. In ordinary experience, you interact in ways that collapse them into localized particles, giving the illusion of solidity. But fundamentally, you are a wave. And like all waves, you exist in a delicate superposition, constantly collapsing and reforming through interaction with the world. Wave and particle are not contradictions. They're complementary truths, both real, both essential, both part of the strange quantum dance that creates everything. Now, let us go deeper still. We've seen that particles are excitations in fields. But what does that mean? How do fields give rise to wave-particle duality? Chapter 7. Fields and excitations. The deeper truth. We've journeyed through the history of wave-particle duality, from Young's double-slit to Bohr's complementarity. But there's a deeper layer to this story, one that connects everything we've learned back to the quantum fields we explored earlier. The resolution of wave-particle duality lies not in choosing between wave and particle, but in recognizing that neither is fundamental. What's fundamental is the field. Let us explore how quantum field theory makes sense of the wave-particle mystery. What is a quantum field? Recall from our earlier journey. A quantum field is an entity that permeates all of space, existing even in empty vacuum. Every type of particle has an associated field: the electron field, the photon field, electromagnetic field, the quark fields, and so on. These fields are not static. They're dynamic quantum systems in their own right, described by wave equations similar to Schrödinger's equation but extended across all space. A field has a lowest energy state called the vacuum state or ground state. In this state, the field is quiescent. No particles exist. But the field is not zero. It's in a quantum state of minimum energy, with quantum fluctuations constantly rippling through it. When energy is added to the field, it transitions to an excited state. A single quantum of excitation is what we call a particle. A photon is a quantum of the electromagnetic field. An electron is a quantum of the electron field. A quark is a quantum of the quark field. So particles are not separate entities moving through fields. Particles are the fields. How fields exhibit wave-particle duality. Here's the key insight. Quantum fields are wave-like, but their excitations are detected as particles. The field itself obeys a wave equation. It has amplitude, phase, and can interfere. When you prepare the field in a state with definite momentum, a plane wave state, it extends across space, wave-like behavior. But when the field interacts with the detector, energy is exchanged in discrete quanta. The detector clicks. You measure a localized particle, not a spread-out wave. This is why photons exhibit both behaviors. The electromagnetic field is a wave. It can spread, diffract, and interfere. But when it's measured, you always detect discrete photons, each carrying a quantum of energy, E equals hf. Similarly, the electron field is wave-like, described by Dirac's equation, the relativistic version of Schrödinger's equation. An electron in a definite momentum state is a plane wave extending across space. But when you detect it, you find a localized particle with definite charge and mass. Wave-particle duality is thus a consequence of the field's dual nature: wave-like dynamics, particle-like interactions. In quantum field theory, the mathematical description involves operators that create and annihilate particles. The creation operator takes the field from a state with n particles to a state with n plus 1 particles. It creates a particle, or more accurately, it excites the field to a higher energy state. The annihilation operator OIS does the opposite. It lowers the field's energy, destroying a particle. These operators act on the field's quantum state, which is described not as a wave function psi of x, t for a single particle, but as a state vector, or as P-ized. in an infinite dimensional Hilbert space representing all possible field configurations. When you prepare the field in a state with a definite number of particles, you use creation operators repeatedly. A dagger creates one particle. A dagger saw 1 creates 2 particles. A dagger saw 2 creates 3 particles, and so on. Plotwalzor creates 2, and so on. But here's the important part. The field state is still a superposition of waves. Even a single particle state is described by a wave function spread across space. The particle is not localized until measured. Quantum fields and de Broglie wavelength. De Broglie's wavelength formula, lambda equals h over p, emerges naturally from quantum field theory. A particle with definite momentum p corresponds to a plane wave in the field with wave vector k equals p over h bar. The wavelength is lambda equals 2, pi over k equals h over p. So de Broglie's formula isn't an added assumption, it's a consequence of the field's wave-like nature. Excitations in the field with definite momentum are plane waves with wavelength determined by that momentum. When you send an electron through a double slit, you're preparing the electron field in a state that's a superposition of plane waves. The field spreads through both slits, interferes with itself, and creates a probability distribution for where the electron will be detected. Upon detection, the field state collapses or decoheres, we'll get to that, and a localized interaction occurs. You measure a particle at a specific point even though the field was spread out. Virtual particles and quantum fluctuations. One fascinating consequence of quantum fields is the existence of virtual particles, temporary excitations of the field that pop in and out of existence due to quantum uncertainty. Heisenberg's uncertainty principle applies to energy and time, delta E delta T greater than or equal to h bar over 2. This means that for very short times delta T, energy conservation can be violated by an amount delta E. The field can temporarily borrow energy to create particle-antiparticle pairs, which then annihilate, returning the energy. These virtual particles are not directly observable, but they have measurable effects. They contribute to the Lamb shift, a tiny correction to atomic energy levels, the anomalous magnetic moment of the electron, and the Casimir effect, a force between uncharged plates in vacuum. Virtual particles are not particles in the usual sense. They're quantum fluctuations in the field, brief ripples that exist for fractions of a second, too short-lived to be detected directly, but real enough to affect other particles. This reinforces the field view. Particles are not fundamental. Fields are fundamental, and their fluctuations, real and virtual, give rise to everything we call matter and forces. Let's make this concrete with photons. The electromagnetic field can be decomposed into modes, wave patterns labelled by wave vector k and polarization. Each mode acts like a quantum harmonic oscillator, with energy levels E equals n plus 1/2, h bar omega, where n is the number of photons in that mode, and omega equals ck is the angular frequency. N equals 0 is the vacuum state, no photons, but the field still has 0-point energy, 1/2 h bar omega. N equals 1 is a single photon state. The field is excited by 1 quantum. N equals 2 is a 2-photon state, and so on. When you prepare a single photon state in a mode with definite k, you've prepared a plane wave with wavelength lambda equals 2 pi over k equals h over p. This wave spreads across space, wave-like behavior, but when it interacts with an atom, the atom absorbs the entire photon. The field drops from n equals 1 to n equals 0, and the atom gains energy h bar omega. The interaction is localized, discrete, particle-like behavior, so the photon is neither wave nor particle. It's an excitation in the electromagnetic field. exhibiting wave properties when free and particle properties when interacting. Similarly, electrons are excitations in the electron field, governed by the Dirac equation. The electron field is a bit more complicated because it's a fermion field, not a boson field like the electromagnetic field. Fermions obey the Pauli exclusion principle. No two fermions can occupy the same quantum state. This is encoded in the mathematics through anti-commutation relations for the electron's creation and annihilation operators, but the basic picture is the same. The electron field pervades space, and electrons are quantized excitations of this field. An electron in a definite momentum state is a plane wave in the electron field. When measured, it's found at a specific location with probability determined by the field's amplitude. All the strange behaviors we've discussed, interference, tunneling, superposition, arise from the wave-like nature of the electron field. Why does measurement collapse the wave function? This brings us to the deepest mystery. Why does measurement cause the field to collapse into a localized state? In standard quantum mechanics, this is called the measurement problem. The wave function evolves smoothly according to Schrödinger's equation, spreading and interfering, but upon measurement it instantaneously collapses to a definite outcome. Why? No one fully knows. There are many interpretations. Copenhagen. Measurement is fundamental. Don't ask what happens, just calculate probabilities. Many worlds. The wave function never collapses. All outcomes occur in separate branches of reality. Objective collapse. The wave function actually collapses, triggered by physical processes like gravity or complexity. Pilot wave, Bohmian mechanics. Particles have definite positions guided by the wave function, which never collapses but guides particle motion. A. Quantum Bayesianism, Cubism. The wave function represents knowledge, not reality. Collapse is updating knowledge, not a physical process. Each interpretation has strengths and weaknesses, but all agree on the predictions, the probabilities of different outcomes, because they all use the same quantum mechanics. For our purposes, the key point is this: whether the field truly collapses or we merely transition to a different branch, the result is the same: wave-like behavior before measurement, particle-like detection afterward. Let this vision settle. The universe is not made of particles, it's made of fields, vast, interconnected, wave-like entities permeating all of space. You're not a collection of particles. You're a pattern of excitations in these fields, ripples in the electron field, the quark fields, the electromagnetic field, all interwoven, interfering, creating the structure you call your body. And those ripples are not solid. They wave, they spread, they exist in superposition, collapsing moment by moment as you interact with your environment, creating the illusion of solidity, of definite position, of particles. But beneath that illusion, you're a wave in the quantum field, dancing with all the other waves, creating reality through constant interaction. Now, let us turn to an even stranger question. If everything is fundamentally wave-like, why does the world appear classical? Why don't we see macroscopic superpositions and interference? Chapter 8. Everything waves. You, stars, reality. We've established that electrons, photons, and atoms wave. But what about larger objects? What about molecules, viruses, bacteria? What about you? The answer, according to quantum mechanics, is that everything waves. Every object, no matter how large, has a de Broglie wavelength and, in principle, can exhibit wave behavior. But there's a catch. For macroscopic objects, the wavelength is so incredibly small and the wave behavior so fragile that it's essentially impossible to observe. let us explore the boundary between quantum and classical, the realm where wave behavior fades and particle behavior dominates. The de Broglie wavelength of everyday objects. De Broglie's formula applies to everything. Lambda equals h over p equals h over mv. For a photon or electron, the wavelength is significant. Nanometers to micrometers, comparable to atomic scales. But for a baseball, 0.145 kilograms, thrown at 40 meters per second, lambda approximately equals 10 to the negative 34th meters. This is a billion times smaller than a proton. At such scales, no conceivable apparatus could detect wave behavior. The baseball behaves purely classically. For a human, 70 kilograms, walking at 1 meter per second, lambda approximately 10 to the negative 36 meters, even smaller. For all practical purposes, macroscopic objects have zero wavelength. They don't wave, but fundamentally, mathematically, they do. The wave function exists. It's just enormously sharply peaked in position space, giving the object a nearly definite location. And the wavelength is so tiny that no experiment could resolve wave effects like diffraction or interference. Where is the boundary? So where does quantum behavior end and classical behavior begin? Is there a sharp boundary or a gradual transition? Experiments over the past few decades have pushed the boundary to larger and larger systems. In 1999, as mentioned, Anton Zeilinger's group demonstrated interference of C60 fullerene molecules, buckyballs, containing 60 carbon atoms, 720 nucleons total. In 2011, researchers demonstrated interference of molecules containing over 400 atoms, including complex organic molecules like porphyrins, important in biological systems, and phthalocyanines, used in dyes. In 2019, a team in Vienna demonstrated interference of molecules with molecular mass exceeding 25,000 atomic mass units, molecules so large they approach the size of small proteins. These experiments push the boundary of quantum behavior to unprecedented scales. Yet even these large molecules are far smaller than a bacterium, millions of atoms, let alone a human, 10 to the 28th power atoms. As systems get larger, wave behavior becomes harder to observe, not because the waves stop existing, but because maintaining quantum coherence becomes nearly impossible. Quantum coherence and decoherence. For wave behavior to be observable, the system must maintain quantum coherence, a delicate state where the different parts of the wave function remain in a definite phase relationship, able to interfere. Coherence is fragile. Any interaction with the environment, scattering photons, colliding air molecules, coupling to vibrational modes, can destroy coherence, a process called decoherence. Decoherence doesn't destroy the wave function entirely, but it entangles the system with its environment in such a way that interference effects are suppressed. The system behaves classically, even though it's still described by quantum mechanics. For macroscopic objects, decoherence is nearly instantaneous. A dust grain floating in air decoheres in less than 10 to the minus 20 seconds due to collisions with air molecules and scattering of thermal radiation. For a human, decoherence is essentially immediate, far faster than any timescale we can perceive. So we never observe ourselves in superposition, even though, mathematically, the wave function encompasses all possible positions. We'll explore decoherence in depth in the next chapter. For now, understand that wave behavior doesn't stop. It's just drowned out by interaction with the environment. Schrödinger's cat. The famous thought experiment of Schrödinger's cat illustrates the puzzle. Imagine a cat in a sealed box with a quantum device, a radioactive atom that has a 50% chance of decaying in 1 hour. If it decays, it triggers a mechanism that releases poison, killing the cat. According to quantum mechanics, before you open the box, the atom is in a superposition. 50% decayed, 50% not decayed. This superposition entangles with the poison mechanism, then with the cat. So is the cat in a superposition of alive and dead? Standard quantum mechanics says yes. The cat's wave function is a superposition of alive and dead until you open the box and observe. But this seems absurd. Cats are not observed to be in superposition. You open the box and find the cat either alive or dead, not both. The resolution lies in decoherence. The cat is constantly interacting with air molecules, photons, its own body heat, billions of environmental interactions per second. These interactions entangle the cat's quantum state with the environment, effectively measuring the cat's state continuously. The superposition collapses almost immediately, not when you open the box, but microseconds after the poison is released, or not released. The cat is never observed in superposition because the superposition never persists long enough to be observed. So macroscopic superposition is not forbidden, it's just incredibly short-lived. Can we create macroscopic superpositions? Some experiments have succeeded in creating brief superpositions of relatively large objects by isolating them from their environment. In 2010, researchers demonstrated quantum superposition of a mechanical resonator, a tiny vibrating aluminum membrane, visible to the naked eye, containing about 10 to the power of 13 atoms. By cooling it to near absolute zero and isolating it in vacuum, they created a superposition of vibrational states. This was a significant achievement, but it's still far from a cat. And the superposition lasted only milliseconds before decoherence set in. Creating superpositions of larger objects requires extreme isolation, ultra-high vacuum, temperatures near absolute zero, shielding from all electromagnetic radiation. Even then, the superposition is fragile and short-lived. For something as large and warm as a cat or a human, maintaining superposition is essentially impossible with current technology. Decoherence wins. So, do you wave? Mathematically, yes. You're described by a wave function, an incomprehensibly complex wave function involving 10 to the 28th particles, but a wave function nonetheless. In principle, if you could be perfectly isolated from your environment and sent through a sufficiently large double-slit apparatus with slits separated by perhaps a centimetre, you would interfere with yourself, producing an interference pattern. But in practice, this is impossible. You're constantly interacting with photons. You're warm, you emit thermal radiation. Air molecules, you breathe, you collide with air. Gravitational fields, you couple to the Earth's gravity. And your own internal processes, metabolic reactions, neural activity. These interactions decohere your wave function essentially instantaneously. You collapse into a definite position billions of times per second, faster than any timescale you can perceive. So you wave, but you never observe yourself waving. By the time you could observe it, decoherence has already destroyed the coherence. You are wave and particle, but the wave is so thoroughly collapsed by environmental interaction that you perceive only the particle, stars, planets, galaxies. What about even larger systems? Do stars wave? Do galaxies? Again, mathematically, yes. Every system has a wave function. A star, described by quantum mechanics, is in a superposition of all possible configurations, all possible positions, velocities, internal states. But the star is so massive, so warm, so thoroughly entangled with its environment, that its wave function is effectively classical. The superposition collapses into a nearly definite state almost instantaneously. The same applies to planets, galaxies, clusters of galaxies. All are quantum systems described by wave functions, but all are so massive and so entangled with their surroundings that they behave classically. The universe as a whole, the entire cosmos, also has a wave function according to quantum cosmology. This is the universal wave function, representing the quantum state of everything that exists. But interpreting this wave function is challenging. What does it mean for the universe to be in superposition? Superposition relative to what? If there's no external observer, how does the wave function collapse? These are deep, unresolved questions in the foundations of quantum mechanics and cosmology. So we live in a strange duality. Fundamentally, everything is quantum, described by wave functions, existing in superposition, interfering and entangling. But practically, large systems behave classically. Definite positions, definite properties, no interference. This is not a failure of quantum mechanics. It's a success. Quantum mechanics predicts that large, warm, interacting systems will decohere and appear classical. And that's exactly what we observe. The classical world we experience is not separate from the quantum world. It emerges from the quantum world through decoherence and the suppression of interference effects. We are quantum beings living in a quantum universe, but we're so large, so warm, so thoroughly entangled with our environment that we perceive a classical facade overlaying the quantum reality beneath. As you settle deeper into stillness, imagine yourself as a quantum wave, vast, spread across space, encompassing all possible positions, all possible states, but interacting constantly with trillions of environmental degrees of freedom. Each photon that bounces off your skin, each air molecule that collides with you, each gravitational tug from the Earth, collapses a tiny bit of your wave function, localizing you, making you definite. Moment by moment you are collapsing and reforming, wave to particle to wave to particle, billions of times per second, so fast that you perceive only continuity, only solidity. But underneath, you are a wave, dancing with the universe, interfering with everything around you, creating reality through constant interaction. And now, let us explore the mechanism that bridges quantum and classical. Decoherence, the process that hides the wave and reveals the particle. Chapter 9. The quantum classical border. We've seen that everything waves, but we don't observe macroscopic wave behavior. The reason is decoherence, the process by which quantum systems lose their coherence and begin to behave classically. Decoherence is not part of standard quantum mechanics. It emerges when you account for the system's interaction with its environment, and it's the key to understanding why the quantum world appears classical at large scales. Let us explore decoherence carefully, for it reveals the boundary between the strange quantum realm and the familiar classical world. What is decoherence? Imagine an electron prepared in a superposition of two locations. Pseudus equals her left plus right. If the electron is perfectly isolated, this superposition persists. The electron is neither left nor right, but both simultaneously. If you set up an interference experiment, the two components of the wave function will interfere, producing observable effects. But now suppose the electron interacts with its environment. Say, a photon scatters off it. The photon carries away information about the electron's location. If the electron is on the left, the photon scatters one way. If the electron is on the right, the photon scatters a different way. The photon becomes entangled with the electron. Ses equals left. Photon scattered left. plus right, photon scattered right. Now the electron state is not a simple superposition. It's entangled with the photon. The two components left and right are no longer coherent, they're correlated with different photon states. If you try to observe interference, you find that the interference terms vanish. The electron behaves as if it's either left or right, not both. This is decoherence. The system's superposition is still there mathematically, but it's hidden in the correlations with the environment. For practical purposes, the system behaves classically, as if it's in a definite state, not a superposition. Decoherence is not collapse. It's important to distinguish decoherence from wave function collapse. Collapse, in the Copenhagen interpretation, is a sudden, discontinuous process where the wave function jumps from a superposition to a definite state upon measurement. Decoherence is a continuous, gradual process where the system becomes entangled with its environment, suppressing interference without requiring collapse. Decoherence doesn't solve the measurement problem entirely. It explains why superpositions are unobservable in practice, but it doesn't explain why we experience definite outcomes rather than remaining in superposition with the environment. Still, decoherence provides a mechanism for the emergence of classicality. Large systems decohere so rapidly that they appear classical on any timescale we can observe. How fast is decoherence? Decoherence timescales depend on the system's size and its coupling to the environment. For a dust grain, 10 to the minus 6 meters, in air at room temperature, decoherence occurs in about 10 to the minus 23 seconds, 100 million times faster than the time it takes light to cross an atom. For a larger object like a bacterium, decoherence is even faster. For a human, it's essentially instantaneous, far shorter than any time interval we can perceive or measure, so macroscopic objects are perpetually in a state of decoherence. We never observe them in superposition because superposition doesn't last long enough to observe. But for microscopic systems, electrons, atoms, small molecules, decoherence can be slow if they're isolated from the environment. In ultra-high vacuum, at ultra-low temperatures, quantum coherence can persist for seconds, even minutes, long enough to perform quantum experiments. This is the basis of quantum computing. A quantum computer manipulates quantum bits, qubits, in superposition. The challenge is to perform computations faster than decoherence destroys the superposition. This requires extraordinary isolation from the environment, hence the need for dilution refrigerators, cooling qubits to millikelvin temperatures. One way to think about decoherence is that the environment is constantly measuring the system. Every photon that scatters off an object, every air molecule that collides with it, every interaction with a thermal bath, carries away information about the object's state. This information is recorded in the environment, effectively collapsing the object's wave function relative to the environment. But the information is irreversibly lost, dispersed among countless environmental degrees of freedom. We can't track every air molecule or every scattered photon, so we can't reverse the decoherence and recover the superposition. This is why decoherence is irreversible in practice. Once information leaks into the environment, it's essentially gone, and with it goes the quantum coherence. Decoherence doesn't turn all quantum states into classical ones indiscriminately. It selects certain states called pointer states that are robust against decoherence. Pointer states are eigenstates of the interaction with the environment. They're the states that don't change much when the environment interacts with the system. For position, the pointer states are localized positions. An object at a definite location interacts with the environment in a consistent way. Photons scatter the same way every time, so position becomes a robust classical-like property. For momentum, the pointer states are different, delocalized plane waves. But position pointer states dominate for macroscopic objects because interactions with the environment, photon scattering, molecule collisions, primarily depend on position. This is why macroscopic objects appear to have definite positions. Decoherence selects position as the preferred basis, suppressing superpositions of different positions. So the classical world, a world of objects with definite positions, definite properties, emerges from quantum mechanics through decoherence. The pointer states, selected by environmental interaction, are what we perceive as classical reality. A related idea is quantum Darwinism, proposed by Wojciech Zurek. It suggests that the states we perceive as classical are those that proliferate many copies of their information into the environment. When a photon scatters off an object, it carries information about that object. If many photons scatter, they all carry redundant copies of the same information. This redundancy makes the information accessible. Many observers can independently access copies of the information without disturbing the original. In contrast, quantum superpositions don't proliferate information redundantly. Different components of a superposition imprint different information on the environment, but the information is fragile and not redundant, so the states we perceive, the classical properties, are those with high redundancy in the environment. Decoherence and redundancy together select the classical properties we observe. Why is the world classical? So here's the answer to the question. Why does the world appear classical, even though it's fundamentally quantum? Because we're large, warm, and thoroughly entangled with our environment. We decohere so fast that we never observe quantum superpositions. The quantum wave behavior exists, but it's completely hidden by decoherence. The classical world is an emergent property of quantum mechanics at large scales. It's not a separate reality, it's a facade, a simplification that emerges when quantum systems interact with complex environments. Underneath, everything is quantum. The wave function never truly disappears, but for practical purposes, large systems behave classically, with definite positions, definite momenta, and no observable interference. This is why we don't see everyday objects in superposition. Not because quantum mechanics stops working, but because decoherence suppresses the quantum behavior faster than we can observe it. Can we observe the quantum classical transition? Some experiments have probed the transition from quantum to classical by gradually increasing the coupling to the environment and watching coherence disappear. In 2011, researchers at UC Santa Barbara created superpositions of mechanical oscillators and watched them decohere by intentionally coupling them to thermal noise. They observed the gradual transition from quantum interference to classical behavior as decoherence increased. Such experiments confirm that decoherence is the mechanism behind the quantum to classical transition. They also show that the boundary is not sharp. It's gradual, depending on the system's size, temperature, and environmental coupling. Decoherence explains a lot. It explains why macroscopic objects appear classical. It explains why we don't see cats in superposition. It explains the emergence of pointer states, but it doesn't fully solve the measurement problem. It doesn't explain why, when we perform a measurement, we experience one definite outcome rather than remaining in superposition with the measuring device and environment. Different interpretations handle this differently. Copenhagen. Measurement is primitive. Collapse happens when a conscious observer is involved. Many worlds. All outcomes occur. We experience one branch, but other branches exist. Objective collapse. There's a physical mechanism that causes genuine collapse at some scale. Bohmian mechanics. Particles have definite positions guided by the wave function. No collapse needed. Decoherence is compatible with all these interpretations. It tells us how superpositions become unobservable, but it doesn't tell us what happens really, whether the wave function collapses, branches, or is merely describing our ignorance. This is still an open question in the foundations of quantum mechanics. Consider this. You exist at the boundary, the quantum classical border. You are quantum, fundamentally. Every electron, every atom in your body waves, interferes, exists in superposition. But you're so large, so warm, so entangled with the world around you, that your quantum nature is hidden. You decohere billions of times per second, collapsing into the definite solid form you perceive. You're a quantum being who appears classical, not because quantum mechanics stops working, but because it works so well, so thoroughly, that it creates the illusion of a classical world. And now, in our final chapter, let us step back and reflect on what all of this means for reality, for existence, for you. Chapter 10. Living in Superposition. We've journeyed from Young's double-slit to Bohr's complementarity, from de Broglie's matter waves to quantum fields and decoherence. We've seen that everything, light, matter, you, exhibits wave-particle duality, waving when free, collapsing into particles when measured. But what does this mean? Not just for physics, but for life, for consciousness, for existence itself. In this final chapter, let us step back from equations and experiments and contemplate the deeper implications of living in a quantum universe. You're a wave in the field. The first and most profound realization. You're not made of particles. You're made of fields. The electron field, the quark fields, the electromagnetic field, these permeate all of space, rippling with quantum fluctuations. You are a localized pattern of excitations in these fields, a wave packet temporarily coherent, interacting with the world. Every atom in your body is a bound state of quantum fields. Every chemical bond is wave function overlap. Every metabolic reaction is a rearrangement of field excitations. You are fundamentally a wave, vastly complex, thoroughly entangled with your environment, but a wave nonetheless. This is not metaphor. It's the literal description given by quantum field theory, our best understanding of reality at the smallest scales. You are in superposition. Before decoherence, you exist in superposition. Every moment, your wave function encompasses countless possibilities, all the different positions you might occupy, all the different thoughts you might think, all the different futures you might live. These are not separate realities. They're all part of your quantum state, superimposed, interfering, creating a probability distribution for what you will experience next. But decoherence selects. Your environment, light, air, gravity, everything around you, constantly measures you, collapsing your wave function into a definite state moment by moment. So you're in superposition for an instant, then collapse, then superpose again, then collapse again, billions of times per second, faster than you can perceive. What you experience as continuity, as a solid, definite self, is actually a rapid succession of collapses, each one selecting from a vast space of possibilities. You are creating reality. In the Copenhagen interpretation, observation is not passive. Observation collapses the wave function, turning potential into actual, possibility into reality. If this is true, then every time you observe something, see a star, touch a table, think a thought, you're collapsing wave functions, bringing reality into definite form. You're not discovering a pre-existing world. You're participating in creating it, moment by moment, through the act of observation. This doesn't mean you have magical powers. You can't collapse wave functions in arbitrary ways. The probabilities are determined by the wave function itself, which evolves according to quantum mechanics. But within those probabilistic constraints, your act of observation determines which outcome manifests. In this sense, you're not separate from the universe. You're the universe, observing itself collapsing possibilities into actuality. Many worlds, many yous. In the many worlds interpretation, things are even stranger. Every time a quantum event occurs, every time a wave function could collapse into multiple outcomes, it does. All outcomes occur, each in a separate branch of reality. When you measure an electron's position, the universe splits. In one branch, you observe the electron on the left. In another branch, you observe it on the right. Both are real. Both contain a version of you. This means there are countless versions of you living out every possible quantum outcome in parallel branches of the multiverse. You don't experience this multiplicity because you're confined to one branch. You see one outcome, and that becomes your reality. But the other branches exist, with other versions of you experiencing other outcomes. If many worlds is correct, then you're not a single entity. You're a vast ensemble of selves, constantly diverging with every quantum event, each living a slightly different life, experiencing a slightly different reality. The you reading this is just one branch among countless others, and every moment you're splitting further. Some interpretations suggest that consciousness plays a special role in collapsing the wave function. This idea, associated with physicists like Eugene Wigner and John von Neumann, suggests that physical systems alone cannot collapse wave functions, only conscious observation can. The argument: a measuring device is also a quantum system. If it interacts with a particle in superposition, the device itself enters superposition. Then the room enters superposition, the building, the Earth, until the entire universe is in superposition. Collapse only occurs when a conscious mind observes, because consciousness is somehow outside the quantum system, able to see definite outcomes. This view is controversial. Most physicists reject it, arguing that decoherence explains the appearance of collapse without invoking consciousness. But it's a fascinating possibility. If consciousness does collapse wave functions, then you, your awareness, is not merely passive. You're actively shaping reality, determining which quantum branch becomes real through the simple act of being conscious. The quantum self. What does all this mean for the self or identity? In classical physics, you're a collection of particles, definite and localized. Your identity is continuous. The particles that compose you change over time, but there's a continuous trajectory linking past and present. In quantum mechanics, this picture dissolves. You're not particles, you're a wave, existing in superposition, collapsing and reforming moment by moment. Your identity is not a continuous thread. It's a sequence of collapsed states, each one slightly different, linked by the evolving wave function, but not by any classical continuity. And if many worlds is correct, your identity is not even unique. There are countless versions of you, diverging with every quantum event, each one equally real. So who are you? Are you the wave function, encompassing all possibilities? Are you the collapsed state, definite but fleeting? Are you one branch among many? Are you the process of collapsing, the interface between potential and actual? Perhaps you're all of these. Perhaps the question, who am I, doesn't have a single answer in a quantum universe. The freedom of uncertainty. One beautiful consequence of quantum mechanics: the universe is not deterministic. In classical physics, the future is determined by the past. Given the current state of every particle, you can, in principle, predict all future states. Free will is an illusion. Everything is predetermined. But quantum mechanics introduces genuine randomness. When a wave function collapses, the outcome's probabilistic. No amount of information about the past can predict the outcome with certainty. This means the future is open. Not everything is determined. There's room for chance, for spontaneity, for genuine novelty. Whether this rescues free will is debatable. Randomness is not the same as choice. But it at least opens a door, a space where the future is not mechanically dictated by the past. You're not a clockwork machine, grinding through predetermined motions. You're a quantum process, unfolding probabilistically, with outcomes that are genuinely undetermined until they occur. There's freedom in this uncertainty. Not absolute freedom, but a freedom from total determinism. A freedom for the universe to surprise itself. The universe dreams itself. Here's a poetic way to view it all. The universe is a quantum field permeating all space, existing in a vast superposition of all possible states. This is the universal wave function, the quantum state of everything. Within this field, patterns form, localized excitations, bound states, structures. These patterns interact, entangle, collapse, creating the appearance of a definite world. Consciousness arises within these patterns, somehow, mysteriously, not yet fully understood. And consciousness observes, collapses wave functions, brings reality into focus. In this view, the universe is dreaming itself into existence. The quantum field is a dream, a superposition of all possibilities. Consciousness is the dreamer, collapsing possibilities into the story of reality. You are one such collapse. One moment in the universe's dream, briefly definite, soon to dissolve back into possibility. And yet you are also the dreamer. Your consciousness is the universe observing itself, the field collapsing itself, the dream becoming aware of its own dreaming. So as you drift now towards sleep, toward the dissolution of waking consciousness, let this vision accompany you. You're a wave, vast and probabilistic, collapsing moment by moment into the definite form you perceive as yourself. But underneath, you're a superposition, a quantum blend of all possible yous, existing simultaneously until observation selects one. When you sleep, awareness dims. The collapse is slow. The wave spreads, less constrained, less localized. You drift into a state closer to pure superposition, closer to the quantum field itself. And when you wake, you collapse again, reforming into the definite pattern you call yourself, ready to participate once more in the universe's grand quantum dance. You are wave and particle. You are potential and actual. You are one and many. You are the universe, observing itself, collapsing itself, creating itself moment by moment. And that is the nature of reality. Rest now in the knowing that you are part of something vast, strange, and beautiful, a quantum field waving through space, dreaming the cosmos into being. And so we return, gently, from the quantum depths. We've journeyed from light's strange double life to matter's wave-like nature, from Bohr's complementarity to the fields that underlie all existence. We've seen that you, yes, you, are fundamentally a wave in the quantum field, collapsing moment by moment through interaction, creating the solid world you perceive. If this exploration has stirred a sense of wonder, or perhaps a gentle questioning of what reality truly is, I invite you to linger in that feeling, to subscribe and continue these journeys where quantum mysteries meet contemplative calm. or simply to rest in the knowing that you are wave and particle, both potential and actual, both dreamer and dream. This is sleep entangled, where fields wave through space, consciousness collapses probability, and reality emerges from the quantum unknown. Until we meet again beneath the cosmic field, rest easy, knowing that the universe is stranger, deeper, and more beautiful than we ever imagined.